Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. We were last time looking at the second fundamental form and we had come up till here where the curvature is given by this formula. It's the ratio of the second fundamental form to the first fundamental form, and we had set lambda to be a direction which is d alpha 2 by d alpha 1, and if we take a derivative of k with respect to lambda and set it to 0, it gives us two solutions. One gives k max and one gives k min, and those directions are called principal lines of curvature. Now, without so much of a derivation, for one thing we said we are dealing with orthogonal curvilinear coordinates, which means my f is 0. Okay. Then I will say this, that we will deal with only surfaces of revolution. Only surfaces of revolution. Okay, which means for these surfaces of revolution, m will be 0. Okay, so that my fundamental form will acquire, ratio, the curvature will acquire L plus n lambda square by E plus g lambda square, or L d alpha 1 square plus n d alpha 2 square by E d alpha 1 square plus g d alpha 2 square. Okay. Now, as I just said before, if we stay with surfaces of revolution, and what are these? There is in a surface of revolution there is a meridian, a curve that revolves around an axis. Okay. So for example, cylinder, if this is my axis, that's my axis, and this is a line, if I make this line rotate around this axis, okay, then I get a cylinder. As the line rotates around this axis, I get a cylinder. Okay, or a circular plate. This is my axis, and let's say that is my meridian, and this meridian rotates, then I get a circular plate. Okay, or as we saw before, a conical surface. If I have an axis and a slanted meridian, and this rotates around this axis, then I get a conical surface. Okay, so these are surfaces of revolution. For these surfaces of revolution, okay, the meridian if it is made one axis, if we take the meridian as one axis and the rotational direction as a second axis, second curvilinear axis, okay, second curvilinear coordinate. These are the principal lines of curvature. These are the principal lines of curvature. Okay, that means one gives you the K max, kappa max, the other gives you the kappa min, and M is 0. Okay, so this is, that's what happens. Okay, so we can check this, out. Let's see, we'll check this out on the next page. Let's say we take again our circular plate, circular plate. So this is my axis and this is the meridian which rotates. Okay, then the meridian I take as one axis r and the other is theta. Okay, so that what is my location vector? This is the vector, this is the coordinate, don't confuse. So we have r cos theta I plus r sin theta j. Okay, so that my del r by del r is equal to cos theta I plus sin theta j, and del r by del theta is equal to minus r cos theta I plus sin theta I plus r cos theta j. Okay, so now if we look at twice of m, which is del r del alpha 1 dotted with del n del alpha 2 plus del r del alpha 2 dotted with del n del alpha 1. In the current form, it is del r dotted with del n del theta plus del r del theta dotted with del n del r. So we need n now. Okay, so we need n. So what is n? Is so we have to do a cross product ijk cos theta sin theta 0 minus r sin theta r cos theta 0. Okay, we have to do a cross product. So that gives me I times this and this is 0, j times this and this is 0, k times r, sorry, what is it, k hat times r cos square theta plus r sin square theta, which is equal to k hat r. Okay, so that the magnitude of r k hat is r. Okay, so now what is the unit vector? Okay, the unit vector is k hat. N is k hat. Unit vector is k hat. Okay, so now if n is k hat, then del n del theta, del n by del theta is 0, del n by del r is 0. Okay, so therefore m is equal to 0, which is what we said. Okay, if the meridian itself is taken as the one of the coordinates. Okay, we'll check this out for a cylinder. Okay, so to remind ourselves, there was this cylinder, then I took the axis as x, then I have a y, and then I have a z, and then I am looking at a point here, and theta is measured from z, so that my r x comma theta was equal to xi hat plus a sin theta j plus a cos theta k. Okay, then a1 was equal to 1 and a2 was equal to a. Okay, so now I have to check this part out, m is 0 or not. Okay, so I need to look at del r by del x, which is equal to I, then del r by del theta, okay, which is equal to a cos theta j minus a sin theta k. That is one part. Okay. Now I need to find the normal. Okay, let me switch. I need to find the normal. Okay, let us mind ourselves that del r by del x is equal to I del r by del theta is equal to a cos theta j minus a sin theta k. So I need to do del r by del x crossed with del r by del theta and divide by the magnitude of that. That's what I need to do. So let's do the cross product. I j k, then I have 1 0 0 0 a cos theta minus a sin theta. Okay, so get this into 0, this j into minus a, so I have minus of j into minus a sin theta. From the rules of cofactor, j gets a minus plus k hat into a cos theta. That is the cross product. Okay, so then the magnitude. Magnitude is a square sin square theta plus a square cos square theta square root, which is equal to a. Okay, and therefore d normal is given by sin theta j plus cos theta k. Okay, so now we have to check for m. We have to check for m. So we have del r del x and del r del theta here. Del n del x equal to 0 and del n del theta is equal to cos theta j minus sin theta k. Okay, so now if I do del r del x dotted with del n del theta, it is 0. Okay, it is 0. I is orthogonal to j and k, and if I do del r del theta dotted with del n del x, del n del x is 0, so that is 0. So that means my m is 0. Okay, so here also what did I do? I took the meridian. I took the meridian as one axis, and as it rotates I took, okay, as it rotates, so I took theta, that as theta, this as x. Okay, then therefore m is 0, and these are the principal lines of curvature. Okay, now we can do one more thing. Lambda was written as d alpha 2 by d alpha 1. So now when we take the lines of curvature and we take the lines of curvature as the coordinates, okay, that means in one case d alpha 2 will be 0, in one case d alpha 1 will be 0, okay. Those are the two directions, right. In one case if I have I and j, I moves j is constant, j moves I is constant, okay. So then what I have is for my kappa I have L d alpha 1 square plus n d alpha 2 squared by E d alpha 1 squared plus G d alpha 2 squared, okay. So if d alpha 1 is set to 0, then I get curvature as n over G, okay. What is n over G, what is n and what is G? So n over G will be del r by del theta dotted with del n by del theta divided by G, okay. So del r by del theta is equal to a cos theta j, okay, minus a sin theta k. I am taking it from here. Then del n del theta I will take it from here, okay. So del n del theta is that. So the dot product of these two gives me, if I dot this and this, it gives me, okay, implies I am saying a cos square theta plus a sin square theta, which is equal to a, okay, and G is equal to a square, okay. G, why is that? Because G is equal to del r by del theta magnitude squared, okay. So del r by del theta magnitude is a square cos square theta plus a square sin square theta root, which is a and square, okay, a squared. This is equal to a squared, okay. You dot it with this, with itself, it's a squared. So if I divide this by a squared, I get 1 over a. So the kappa curvature is 1 over a, or the radius of curvature is a. Radius of curvature is a, which is true, right. D alpha 1 is dx. So this curvature in this direction, or radius of curvature in that direction, is a. This is a, okay. And similarly, if we set d alpha 2 or d theta to 0, okay, then we get kappa as equal to L over E, okay, which is equal to del R by del X dotted with del N by del X divided by E, which is a1 squared, okay. Now del N by del X is 0, so this is actually 0, kappa is 0, which means the radius in the one direction is equal to infinity, which is also true. So if I have a cylinder, and how is it formed? It's formed by this meridian, okay, and this is my axis, and it rotates and forms a cylinder. Then the radius of curvature related to this is infinity, the straight line is infinity, which is r1, and the radius of curvature related to alpha 2 theta is a. Okay. So for surfaces of revolution, if we take the meridian and the angle as the coordinates, we will have m as 0, and these are the principal lines of curvature. There are proofs, okay, not okay. It's unimportant to. So that's all we need. So we are going to deal with surfaces of revolution. If we are going to deal with curved surfaces, these are surfaces of revolution, and we will take the meridian and the angle as our coordinates, and those are the principal lines of curvature. Okay, that's all we need for now. Okay, now we need one important result, which I will take it up. Time is kind of running out, so let me just start the process and we'll continue from the next class. So there, in the process of deriving our equations of motion, okay, or let me just spell out the procedure. We have so far seen an elemental length, okay, as a1 square d alpha 1 squared plus a2 squared d alpha 2 squared. So that's a surface, elemental length on a surface. Now we'll be dealing with thin shells, okay. So we will be dealing with shells which will have a middle surface, okay, which will have a middle surface, and we will describe everything: displacement, strain, okay, and so on, in terms of the middle surface and its properties. Okay, so this is an elemental length on the middle surface. Then we will take up, if I expand this, enlarge this, this is my middle surface, which has these properties a1, a2, r1 and r2, okay, and there is a thickness, okay. So this middle surface carries the alpha 1, alpha 2 coordinates, the other dimension thickness carries the alpha 3, okay. So now at every point on this middle surface there is a coordinate system, alpha 1, alpha 2, alpha 3. So next what we will do is we will describe a point within the material. Okay, we will describe a point within the material. So this is my middle surface. So we will describe a point within the material away from the middle surface. So this is the middle, so some point over here in the alpha 3 direction. So let's say this is alpha 1, this is alpha 2, this is in the alpha 3 direction. So somewhere in the thickness we will describe a point. Okay. So that will carry alpha 1, alpha 2 and alpha 3 coordinates. Then we will take another neighboring point which is alpha 1 plus d alpha 1 away, or which is at, then alpha 2 plus d alpha 2 and alpha 3 plus d alpha 3, and we will form the basic length again. We will call that ds dash whole square, just like this. Okay. So it will also carry a1, a2 and so forth, but it has a different form. Okay, ds dash square. Then on that, from this ds dash we will go to ds dash original length, and we will describe elongation or strain of this element, some element between 2 points infinitesimally away from each other. Okay, elongation. Then from there we will describe strain. From there we will use Hooke's law and some assumptions, Love's assumptions. Okay, to relate stress and strain. Stress and strain. Okay. From here we will form the strain energy. Okay. From the other side we will look at the kinetic energy of an element and the total material, total structure, through integrals over the structural dimensions. Okay. Then we will subject it to Hamilton's law. That is the idea. All the while a general surface, a general curvilinear surface is assumed. Surface of revolution if it is curved. Okay. And so everything will be in terms of the general formula A1, A2, R1, R2. We will not specify this till the end. So this will be a general surface. Once Hamilton's law is applied and we get our equations of motion, okay, then if we substitute A1, A2, R1, R2, suppose related to a cylinder, then out will come equations of motion particular to a cylinder. And if we substitute these parameters that are meant for a circular plate, then out will fall equations, dynamic equations of motion for a circular plate. So these are very general equations in that sense. So we will follow that process. Along the way, somewhere here we will need something called Gauss-Codazzi relations for a surface. Okay. So instead of deriving them when I need it, I will do it in advance, okay, in the next class. Right now the time is up, so I will close here. Thank you.